minimum 1 hour तो करना ही है.
वो तो होगा.
Okay, so I have now started the recording the session.
Okay.
Good evening to all of you. Myself, Professor Dharmesh Rai Kundalia, Head Department of Statistics, Sardar Patel University. So first of all, happy National Statistic Day to all of you. We, the Department of Statistics of Gujarat, have started a online lecture series on the contribution of Professor C.R. Rao. So on the occasion of a National Statistic Day 2026, we have the esteemed speaker is Professor K. Muralidharan, who is going to talk about the Rao Score Test and its application, which is the major contribution of the Professor C.R. Rao. Professor Muralidharan sir is our alma mater. He is alumni of Department of Statistics, Sardar Patel University, and he is currently the first senior professor of statistics as far as concerned to the state of Gujarat. So let us congratulate the Professor K. Muralidharan for his senior professorship. For detail, I request our coordinator of this program, Dr. Kimia Tinani, to introduce the today's speaker, Professor K. Muralidharan. Kimia madam, please.
Respected our distinguished speaker, Professor K. Muralidharan sir, respected Professor and Head Dr. Dharmesh Rai Kundalia, Professor Jyoti Devecha Madam, Professor and Head Aarti Rajagurya, Veer Narmad South Gujarat University Madam, Professor Kalpesh Taylor from Bhavnagar University, faculty members, research scholars, dear students, and all the participants joining us online, a very warm good afternoon to you. It is my great honor and privilege to introduce our distinguished speaker for today's lecture, Professor K. Muralidharan sir. Professor K. Muralidharan sir is currently serving as a senior professor and former head of Department of Statistics, Faculty of Science, the Maharaja Sayajirao University of Baroda. He also served as a Director of Population Research Center at MSU Baroda from 2011 to 2016 and was an adjunct professor at IIT Gandhinagar from 2012 to 2015. He completed his MSc in Statistics with first rank from Calicut University and his MPhil and PhD in Statistics from Sardar Patel University, and completed his postdoctoral fellowship at the Institute of Statistical Science, Taiwan. He is also an internationally certified Six Sigma Master Black Belt and quality trainer from the Indian Statistical Institute, Bangalore. Professor Muralidharan sir has more than 33 years of teaching, research experience, and has guided 7 scholars and published more than 150 research papers in reputed national and international journals. His research interests include statistical inference, applied stochastic point process models, reliability and live testing, industrial statistics, artificial intelligence, and machine learning, quality and Six Sigma. His outstanding contributions have been recognized through numerous honors. He is a Fellow of Royal Statistical Society, London, Fellow of Indian Society for Probability and Statistics, Fellow of Gujarat Science Academy, and nominated member of National Academy of Science, India. Among his prestigious awards are the Distinguished Statistician of India Award 2018, the Best Science Teacher Award in Mathematical Science 2017. Professor Muralidharan is author of several books, including best-selling Six Sigma for Organizational Excellence, a Statistical Approach, published by Springer, along with books on parametric inference, quality, reliability, maintainability, and sustainable development and quality of life. He has successfully completed 5 major research projects funded by agencies including UGC, DST, Ministry of Health and Family Welfare. He has delivered more than 190 invited lectures at national and international conference organized by so many events and provided consultancy to leading organizations such as Reliance Industries, TCS, Dubai Electricity and Water Authority, Stockholding Corporation of India. Today, we are indeed privileged to have such an eminent statistician deliver the third lecture in our prestigious lecture series on the contribution of Professor C.R. Rao, his lecture titled Rao Score Test and its application. Sir, on behalf of Department of Statistics, Sardar Patel University, Vallabh Vidyanagar, I extend a very warm welcome to you. We sincerely thank you for accepting our invitation and for sharing your valuable time and expertise with us. Over to you, sir.
Thank you
Muralidharan,
very much, Kimia. Thank you very much.
Thank you,
Thank
sir.
you to Professor Dharmesh Raikundale as well. When he invited me for this particular talk, I immediately accepted. We have a very good friendship, very good relationship, association with SPU as well, Department of Statistics of SPU University as well. So I can't resist or reject his invitation in any case. So I immediately accepted to be a part of this celebration. So today
Thank you.
is very
Thank you, sir.
important
Thank you.
for, it's my pleasure, my pleasure. Today is very important for all of us. We are celebrating the 20th National Statistics Day as a birth centenary of Professor Prashant Chandra Mahalanobis, a very well-known and internationally acclaimed scientist or statisticians per se. And yes,
Muralidharan,
although
sir,
this,
your video is off.
that's what I'm seeing. What happened to my video? I could not see that.
Okay. You can exit and again you can log in.
Let me see.
Perhaps it may
Yeah.
work out.
Show my full video. Show full video. Really interesting. Wait a minute. Background.
Yeah, video is, I think, some problem.
Yeah, there's some problem. Yes, background and article. Framing. Puts your camera into. Oh my God! This is really.
ये जो लैपटॉप है उसमें कैमरा के ऊपर कोई शटर है, क्योंकि हमारा एक बार ऐसा हुआ था.
अच्छा.
शटर
ये
खोल देंगे.
देखो. हाँ, एक मिनट है.
नहीं आ रहा है. यस, आ गए. या क्या बात है, मुंह दिखाई हो गई. वाह,
या वही शटर बनता. शटर ही बनता.
Thank you, Jyoti madam, for giving the idea. Thank you.
Very good. Thank you. Okay, so I'm going to share my presentation. Okay, one of you please let me know if the presentation is visible or not.
Yes, sir. Is visible.
Is it visible? Okay, so it is in the slideshow mode. Is it okay now?
Yes, sir. Yes, perfectly.
Yes, sir.
Okay, I'm in the second slide. Can you see? Can you see it? Second slide?
Yes, sir.
No.
Okay, then fine.
Unable to see.
Perfectly all right. Okay. So as I had mentioned already, today is very important for two reasons. One is our National Statistics Day, and plus the C.R. Rao, the series of lectures started for last 3 or 4 months. Now this is the third talk in the series, if I am correct. And I congratulate SP University Department of Statistics for organizing this and for making me as a part of this celebration. Thank you very much. And just a few words about Professor C.R. Rao, a very well-known and the person who crossed 100 years. So he died at the age of 102 years in 2023. Okay, achieving 102 years. So that itself is a very, very important thing. And his contribution, even I feel so sorry to say that even I'm not a big person of that kind. So, but still, an honor for me to say something about him, something about his contributions rather, because which I have also used in my research. That is score test. Okay, so let me have some important facts about C.R. Rao, because in the last two lectures in the series, people have spoken very detail about Professor C.R. Rao. So I'm not going to do that, but still, okay. So his contributions, has been felt in many of the areas, cutting across statistics, physics, biometry, biostatistics, and a lot of generalized metrics in words and all those things. So he is really a pioneer. He was really a pioneer in statistics. There is no doubt about it. He received a number of awards, including Padma Vibhushan. In earlier, he received in 1968. He received Padma Bhushan as well. And few years ago, he was awarded the Padma Vibhushan as well. Okay, so all other details, as you can see, and then courtesy to Wikipedia, I have gathered all this information from Wikipedia. So I don't want to discuss too much, and anyone can get into and get the details of each and every information there. Okay, so I'm really honored to give a talk in his name rather. Okay, as a series of lectures, which is organized by the statistics group or departmental group of Gujarat. That's really a good initiative. This is the third third in the series. Okay, so today's importance, as I had already mentioned, it is Prashant Chandra Mahalanobis' birthday. Okay, so we are celebrating the 20th National Statistics Day celebration. Another pioneer in this world. Probably the 2-3 people which we can always remember is one of the best person is the Prashant Chandra Mahalanobis, or in short, PC Mahalanobis. He was the statistical advisor to the Prime Minister when Nehru was our Prime Minister, the first Prime Minister of India. Okay, now at that time, he guided, he planned, he instructed how to conduct the small scale and large scale survey for getting the best yield for for people working in the agricultural field and everything. That was his main contribution. So that studies only he brought the Mahalanobis distance. That's really one of the what you say, a peculiar and a unique contribution of Mahalanobis, and is called in the name Mahalanobis distance. And he was the founding director of the ISI in 1949. So he also received a number of awards, including Padma Vibhushan 1968. Okay, so courtesy to Wikipedia, so you can also get the details about all these two guys. Okay, so let me also wish all of you the 20th National Statistics Day celebrations. Thank you very much for giving me an opportunity to do this. Okay, so my talk will be largely inspired by our own books written with Professor B.K. Kale, Parametric Inference and Introduction. And here is the international version of this thing. Probably you may not get the Indian version now because they have stopped publishing, I think. So, but the international version published by Alpha Science is available for purchase also. You can get it into any online marketing and you can get the book. Okay, so this is how the whole content of the presentation is going to be. I'll give you some introduction about the testing of hypothesis, the importance where we need to use the score function and the information function. These two together is a very important combination. It's actually a dual. Okay, contribution. So one of the most important, if you look at the other field of science or any other field, social science, etc. So according to them, the most important contribution of Rao's is the Rao Score Test. So I'm going to discuss that one with some examples on exponential and normal, so that the students. So this particular talk is fully focused on students of MSc and research students. So I request the students also to work on this. Of course, I will share this presentation with all of you. So that is promised. And after the completion of this, I will share with this. And even you can also see the YouTube if it is recorded. So anytime you can open and see the things, because I want you to see, because I am also going to show you some derivations, etc. But you will have to check the corrections. According to me, it's fine, but still, I want you people also to check the results. Okay, so Rao Score Test will be in the center of attraction here. And I will also show you some applications coming in genetics, physics, and plus my own research contribution that's coming under power law process. So I did a series of research publication based on Rao Score Test during my PhD, even after PhD as well. Okay. Let us now see the introduction of this. So I believe all of you have learned the idea of testing of hypothesis, because that is very important, because that I consider to be the basic understanding required for this presentation. Because if you don't know the what is H0 and H1, then the things will not work. At least you should know what is null hypothesis, what is tested, anything which is tested for trueness or tested for its claim, or this thing is called null hypothesis, and anything tested against that is called alternative hypothesis. Notation again is universal, H0 and H1. Yeah, one can use any kind of notation, no issue. I will follow the same notation, H0 and H1 as well. Okay, so it's very, very important. And to test under the null hypothesis for a particular distance, we always need to see what type of errors it is committed. So you have probability type 1 error as alpha, and probability type 2 error as beta. 1 minus beta become the power of the test. Okay, at least some basic concepts, how the hypothesis becomes simple, how it becomes composite, how it can become one-sided, two-sided, etc. Some basic understanding is required to understand this whole talk. Okay, so I believe at least even graduation also we teach statistics, and even for commerce, arts, and even science, of course. Okay, you suppose some of you may not be from science background, some of you can be from arts or commerce. So I'm sure that they are also exposed to the idea of hypothesis. Okay. Now, whether it is a hypothesis setting or you talk about any kind of estimation, likelihood function comes into phase, and that becomes the most important, or the foundation of all this inferential statistics. Okay, so likelihood ratio function or likelihood functions. Okay, it's a very, very important concept in this one. Okay, you may call it as the joint density function. Okay, the moment you call it is likelihood function, it becomes a parametric function, because that is what you are going to maximize or minimize. Depends on the circumstances and the requirement. Okay, so and the likelihood function specifically it is used for three important large sample concepts. That is for constructing likelihood ratio test. Wall test is another important alternative for the likelihood ratio test, and the Rao score test. Interestingly, all this will coincide. All these are going to be same if n is very large, sample size is very large, and under certain regularity conditions. So that is to be stipulated whenever you talk about the likelihood ratio. Likelihood ratio test, you have separate this, because we will have to compute the test value under both null hypothesis and alternative hypothesis. Wall test also have some importance, some regularity conditions to be. At least you should have the derivative exists. At least was two order derivative should at least should be exist. And even Rao score test also we will go up to the second order derivative, because for Fisher information derivation we need second derivative of the likelihood function. Okay, so interestingly all these three are same almost, but the most important part of Rao score test is that we need the calculation of likelihood under H0 only. Okay, that's the beauty of this Rao score test. Okay, so you will definitely understand why, how it is working for many situations. Okay, so let us look at this particular slide. simply reduce the speed of the fan. Okay. Okay. So you have a setup. You have x1, x2, etc. are the random variables coming from a mass function or a probability density function with the theta as the parameter of interest, or the theta characterize the density or the mass function. Okay. It is always unknown. So what you do, you take sample of observations and write down the likelihood. Okay, so L theta is equal to simply product of fxi theta. Please note that I have written L of theta. So theta, so it's become, the moment you say likelihood function, it becomes a parametric function. Okay, so in the joint density, when you talk about it, that is simple probability theory we talk about, that is, it is going to be a function of the data. Okay, so random variables. So score function is the first derivative of the log likelihood. Please note u theta. So please note these one or two notations here. This is because I am going to recall again and again. Okay, the score function is defined as u theta is equal to d by d theta of log L theta. And interestingly, it measures the gradient of the log likelihood. Just imagine you have an equation y equal to a plus bx. So what you get dy by dx, you get the slope, right? So it is just like slope. So it is actually the slope of the log likelihood function. So that is why it is called a gradient. So gradient and a slope, as such, they are same, but context-wise, it will be different. So when you talk about a line, say simply y is equal to mx plus c, or y is equal to a plus mx, or whatever you talk about, the way you. So dy by dx gives you the m, that becomes slope m. So here is just like a gradient is the slope. That's a very, very important thing. So with the inclusion of the slope function, the gradient function, you can construct the test statistics. That is the main contribution of score statistics. Of course, you need Fisher information also. And Fisher information, generally the notation is psi theta. It is actually the expected value of d by d theta of log L whole square. Okay, it is second derivative is taken. Or in a simple form, you can also equate that as minus expected value of d square by d theta square log. And interestingly, Fisher information measures the curvature of the log. Okay. So there is a very important relationship with variance and I. Information functions, variance of theta is always greater than equal to 1 upon I theta. This is obvious from the Kramer-Rao inequality, if you see. Okay, we always construct a variance of the unbiased estimate, variance of t greater than or equal to g dash theta whole square by expected value of d log theta whole square, or minus g dash theta whole square. So that is simply theta. So variance of t gets a very important relationship. So variance, even so u theta, if you take the variance, because expect, okay, expected theta is good, so you can expect u theta square. So that simply become I theta, interestingly. Okay, so relationship, please note textbooks on good. I will not insist you read our own book. You can refer to any book. Again, Clay book is there. Book by Rahaji and Saleh is there. I mean, there are many such interesting books, but slight books I would prefer. Even Wall's book you can consult for all this. Okay, learn the important u theta, I theta, and so interestingly, curvature with this is curvature, that is the parameter uncertainty. And flat
हेलो सर, आपके फोन में नेटवर्क का इश्यू है शायद। Sorry, participant. Due to network issue, sir is left. You have to wait for 2 minutes. So sir will join and we will continue.
Hello, madam, is it okay now?
Yes, sir.
Okay, let me. Okay, is my presentation visible now? Is my presentation visible now?
Yes, yes, sir.
Okay, fine. So where did the problem arise? Previous or the forward one? A. Okay. Okay, shall I continue?
Yes, sir.
Have you seen this?
Sir, from previous slide.
Sir, from next slide.
This one? This one you have seen?
Yes.
This one you have seen?
Yes.
Yes.
Okay.
Yes.
This one you have seen?
Yes. From the
Yes.
Okay. From here. Okay. So okay, fine. No issue. Okay. So as I had already mentioned, the computation of u theta, I theta all involves the first derivative and second derivative. Let us see with an example now. Okay. So okay. So this is where I have to stop. Okay. Now, okay. So the curvature, when I had already mentioned, the steeper curvature means the parameter uncertainty shrinks rapidly, and for a flat curvature, they will have a weak identifiability and therefore high variance. Okay. Now, and the result theta cap ML is always approximated as a normal with theta and 1 upon n times I theta. And this relationship and can be proved also. You can see and refer to any books on statistics for that. Okay, look at this example now. Is it okay now? Just look at the example. All is an exponential distribution is defined with the parameter theta, or you can say the mean is theta in this case, because 1 upon theta e power minus x by theta. If you take the mean, it becomes theta. Likelihood is written there. Log likelihood is also shown there. Look at the computation of u theta. Derivative of log L theta with respect to theta minus n by theta plus 1 upon theta square summation xi. I theta is also shown. And for simplicity, I have shown here a few samples, that is 10 samples of exponential distribution with parameter theta is equal to 5. Summation xi is also computed. So it's simply a plugging in the u theta formula. Okay, so it is coming out to be 0.08. So you can see that this is the slope or the gradient of the distribution. Okay, and I theta is also similar. Now exponential distribution is only one parameter, and look at the normal distribution with parameter both mu and sigma square unknown. Okay, density is shown there, likelihood is also shown there, log likelihood is also shown there, and you get that. There are two parameters, so you will have a score function for mu also, score function for sigma square also. Similarly, Fisher information for mu, Fisher information for sigma square, and cross information for mu and sigma square. Okay, that becomes the covariance kind of thing. So you will have the score vector. Okay, so you can see that u mu and u sigma square, it is simply a column vector. Okay, so and Fisher information matrix and inverse curve. So this is very important because when you take the inverse only, you will come to the variance. Okay, since covariance, you can see the off diagonal elements are 0, so inverse computation becomes very smooth. Okay, so sigma square by n, and we know that the sigma square by n is the variance of x. Okay, x bar, you can say sigma square by n. And the variance of sigma square is 2 sigma raised to 4 by n. This can also be shown with detailed proofs and everything. Okay, and another interesting relationship here you can see is Fisher information multiplied by minimum variance is equal to 1. Now with that, I think I will now define how Rao Score Test is defined and how it works. Okay, I want you people also to check all these quantities and see whether you are also getting the same result. You might have done it already in the inference class. Okay, so please work on with some other distributions also. But many cases when you are dealing with two parameter case, say for example beta distribution, gamma, Weibull, then many such distributions, you won't get an exclusive or close to form expression for likelihood and log likelihoods. Okay, so even likelihood equations, you may need some kind of numerical methods to solve it. So you should do that also. But even for score function also calculation, you may need some kind of numerical calculation. I will show you an example with the gamma also. So it says statistical hypothesis. Very important things. Now from here onwards, I will focus only on Rao's score test. It's a statistical hypothesis test used to determine whether a parameter or a set of parameters significantly improves a model. It's based on a score function, the first derivative. We have already seen it. And the computation also we know. Especially valuable because it requires the estimation only under the null hypothesis. And this is the speciality of Rao Score Test, and this is the uniqueness of Rao Score. All other tests, classical tests you talk about, it all involves somewhere the calculation, even not the most powerful test derived by Neyman-Pearson criteria, that also need the calculation of likelihood under H0 and under H1. And this is where this Rao Score Test comes on the forefront. Okay, so that you can. So this is how it is done. So you have H0 theta equal to theta naught against H1 theta naught equal to theta naught. And the Rao Score Test statistics is defined as S equal to U of theta naught transpose I theta naught inverse U theta naught. Okay, you can always talk about the vector of parameter. That is why it is in matrix notation, U theta naught transpose I theta. If there is only a single parameter, it becomes simply U theta naught square divided by I theta naught in a simple form. Okay, so we have used the same notation, U theta for score and I theta for information function. And under H0, because we need the calculation only under H0, and then under H0, S follows chi-square K approximately, where K is the number of restrictions. So whatever parameters are defined under H0, accordingly, the chi-square will take its degree of freedom. Okay, here is the single parameter case. It becomes simply U theta square divided by I theta. Okay, so here is a simple calculation. Exponential case, we have already computed the score and information. So if you substitute, you get 0.0187. Okay, and under H0, that becomes, if you have to compare with the 3.84. That is the value from the chi-square 1 from at 5% level. So you just compare, it becomes small. So therefore, the hypothesis is accepted. That means there is no evidence against H1. The same way you can talk about any other parameter value you can test under H0. Okay, so let us now look at another application in genetics. Most often you come up with this kind of examples for your research projects and all those things. So let us take a simple example. Here's a very simple example, and a very important example here. So suppose a researcher wanted to determine whether a particular gene variant increases the risk of diabetes. It's very clear whether the patient will have diabetic or not, given the patient have different gene types. Gene types are notated in the form capital A, small a, and small a. So capital A stands for normal allele, and small a stands for very. And the data is like this. So gene type is shown there. So for that, correspondingly, I have given the X variable, that is independent variable, that's 0, 1, 2. This is just a notation for modeling, that's all. You can have 2, 1, 0 also. That is not, this up to you. And the data is diseased and healthy. You can see there are about 20 patients diseased, 80 healthy, and total becomes 100, having capital A as gene type. Similarly, capital A and small a have the 100 genes, where diseased are 35, healthy are 65. Same way, small a allele people have 30 people were diseased, healthy 20, and total 50. So this is how the whole data is going to be. Okay, so you can increase the sample size here. Here it is coming out to be 250 samples. Okay, so what do you model? So how do you model? So naturally, we have to see whether there is a presence of diabetics or not. Okay, given all this data. So naturally, you will go for binary logistic regression. So yi is modeled as y as disease, 0 as healthy. So what you consider? You consider the allele gene type as X, as 0, 1, 2. As you can see the notation 0 for AA, 1 for AA, like that. And so what you model finally, you will have to find out the probability correspond to each presence of each person, whether he has diabetic or not. So probability y is equal to 1. That is denoted as y pi. And probability yi equal to 0 can be written as 1 minus pi. And with any way you can model, can either with 1 or 0. So that's not an issue. So pi. So when you consider this log, pi by 1 minus pi. So pi by 1 minus pi become odds ratio. So what you are ultimately modeling in bivariate logistic regression, you are modeling the log odds ratio as a line, as kind of this. So relationship beta naught plus beta times xi. So that becomes a straight line. So log of odds ratio. So you will have to get the pi. So pi from this relationship you can easily compute as e power beta naught plus beta xi divided by 1 plus e power beta naught plus x beta xi, and that becomes the logistic function. Okay. So what is your interest here? So we have to test h naught beta equal to 0 against beta not equal to 0. So beta equal to 0, if it is accepted, that means there is no effect of alleles. And if beta is equal to 0 is rejected, that means the alleles have, the gene type has the impact on the patient being diabetic or not. Okay, this is how you interpret the once it is absent. Let us see for the same example. Let us do the same computation. So you have yi is a binary variable. So we'll definitely have to go into the Bernoulli distribution. Likelihood is returned there. Log likelihood is returned there. Now substitute the value of pi there, so that we have already obtained there. Then you have the log likelihood equation. Take the derivative of that with respect to beta, because it's now only beta under H0. So beta equal to 0, we can model that as simply pi is equal to p. So that p becomes c power beta naught by, because beta common xi, that becomes absent now. So Fisher information is also computed, and under H0 again I0 is computed. So R score stat is also computed in all in the notational form. Okay, so under H0 as follows chi-square 1 approximately. Okay, so let us do the computation now. So finally, we have to compute that yes, that is summation xi times yi minus p whole square divided by p times 1 minus p summation xi square. And we know how to do it. Okay, here is the same example again. So you have 250 total individuals, and total deceased among them are 20 plus 35 plus 30, 30, that becomes 85. So the proportion of people deceased is become 85 divided by 250, that is 0.34. So with that, now I can compute the expected frequency, that is 100 times 0.34, 100 times point, that is also over. So we can now compute the complete statistics. Score function is computed here. So under H0 it becomes 27. Fisher information is also computed, that under H0 it becomes I0, that becomes finally 67.32. And thus we have score statistics S as 10.83. And the critical value at 5% level is chi-square 1 is 3.85. We have already seen it. Now compare this value, that is test statistics value, that is 10.83 with the 3.84. So naturally it is larger. So we reject the H0. That means the presence of genes, wheel variant is really associated with the diabetic risk. So that is how the usual. So what I want you to see that the simplicity of test calculation or test value calculation. This is where you cannot do the likelihood ratio test or any other test per se. You need at least some kind of numerical calculation or some computationally based calculations. So here it becomes simple and straightforward. So you don't need any what is exactly what is happening in the H1. Okay, the alternative hypothesis, what is the value, we don't need it. So here is another example where I will show you how it becomes difficult when you have when you do not have the closed form expressions. So this is from the same book which I had already shown you, that is parametric inference. So if you see the page number 9.16, 17 and 18, just the page number is given in this format. So look at the page number straightway. You can see an example based on gamma distribution here. So a gamma distribution is defined based on two parameters, alpha and lambda. Now, again, for simplicity only, we have considered the H0 as alpha equal to 1 and lambda equal to 1. So when alpha is, please note that here lambda is called the shape parameter. So when lambda is equal to 1, it becomes exponential. And when alpha becomes 1 again, it becomes a unit exponential. So it's a unit exponential case. All equations, all likelihood equations, score function, it all can be simplified to some great extent. But still it involves some kind of gamma function, digamma function, and trigamma functions, because derivative will also come in. So in the regular usual case, you cannot solve manually. You need a kind of numerical evaluation. But to some extent, I just want you to address this issue. You please refer to the book and see how the score test simplifies the whole theory of proposing test of hypothesis. Okay, for a particular test parameters case. Okay, so finally it is coming out to be n minus summation x, because there's two parameters. Please note. So it's a vector here. So you have a the vector in the first case. You can see n minus summation xi and summation xi. That is the score function correspond to alpha, and summation log xi minus n times psi1 is the score function correspond to lambda. Similarly, you have a Fisher information matrix now, because here you can see that it is all simplified. So you don't need further calculation means you need only a side dash. That side dash one is also it's also psi one is actually called as Euler's constant. Okay, and that is coming out to be value minus gamma, and that value is also known to you. It's a physics constant or mathematical constant, and the value is coming out to be 0.5662 or something like that. Anyone can check. And psi dash 1 is going to be pi square by 6. Please note that all these values can be obtainable from Abramowitz and Stegen gamma distribution table. It's a very big and very healthy, very stout book. So where you will get plenty of results and connection with other gamma, digammas, trigamma, functional relationship, etc., etc. So you should also see to it. SP University has this book. I have seen the book. I have referred to that book from the SP University only. So please see that book. So here again, that equation, that 9.3.2 on the right panel, you can see the equation here. So this is the equation with same score test. This is the same score test. 1 upon n log L d by this is same term which we have discussed. Plus, there are a lot of other interesting properties, and this thing also shown there. It's also shown in this particular. This is how it is connected with the Walsh test, 1943 test. Okay, so now, yes, Walsh test doesn't need any score value, but it requires a Fisher information function. And you can see how under H0 it goes, and asymptotically also how it performs. And so I want you to address. I see this particular books. Okay, let us now quickly see an application from physics. Okay, suppose a physicist is conducting an experiment to detect a new subatomic particle in a high energy collision experiment at an accelerator such as CERN. CERN is actually a nuclear reactor institution in Germany or so. The detector records counts of events. So here is a count of events. So that means it will definitely follow Poisson distribution, because it is also the counts takes place very rarely. So the perfect setting for Poisson distribution, right? So Poisson distribution is used for such kind of modeling situations. So X is Poisson with lambda, and let us say lambda is lambda naught under the background noise. So maybe under H naught you can specify it as lambda naught, but under H1 it becomes lambda naught plus theta. So testing this under H naught lambda equal to lambda naught against H1 lambda naught plus theta is as good as testing H naught theta equal to 0 against theta greater than 0. So it simplifies to a very great extent. Okay, so let us now see how physics, these kind of experiments are very important. They generally do many kind of modeling when there is the presence of noise, and noise against the precision, noise against the accuracy, etc. Signaling the whether it is signal is weak or strong. So that kind of modeling aspects they use. Okay, here is the complete derivation of that. So you have a Poisson distribution, so likelihood can be easily written down. So under H naught theta equal to 0, the U theta score function is calculated. And yes, of course, we have to assume some lambda naught value. In the practical case, I will assume some lambda naught. And yes, what do you mean by U theta when it is evaluated under theta equal to 0? That means it checks whether the observed counts are significantly larger than the expected background counts. And this is very important to understand whether the noise presence is there or not. And Fisher information is also calculated, and also since it is Poisson, it simplifies to a great extent. And score test is also shown there. So here is the data and all those things. You have 10 observations generated from Poisson distribution with the lambda naught is equal to 5. And the observations are shown there. Expected total count is also there, because it's simply n into lambda naught. And U0, I0, and score status is finally is coming out to be 2. And under H naught again, we have only one parameter. So 1 degree of freedom, chi-square value, as you know, 3.84. It is compared to 2 is less than 3.84. We do not reject H naught. That means the observed excess of 10 events is not statistically significant at the 5%. Okay, now if I change the data, what will happen? So let us look at this data now. Okay, so you can see the whole thing changes. So Rao score test data. So what it means actually, that's changing from the original data to this data, 8, 7, 9, 6, 8. So what happened means you have increased the noise actually. Okay, so the presence of noise is very large here. So we reject the and conclude, because here 8 is compared with the 3.84. In earlier case, it was 2 and 3.84 is compared. So there it was accepted, here it is rejected. So we reject and conclude that the observed counts provide stronger evidence for an additional signal beyond the non-background. So this is how the physics people conclude the whole situation. Okay, so now from here onwards, I will take you to a different direction where I will use the score test for my own use. It's already published, actually. A very good journal it was published, Journal of Statistical Theory and Practice. It was a journal of Faith Taylor and Francis, along with one of my colleague, collaborator rather, from Taiwan. Okay, so what is power law process? Now look at this. I have simply cut and pasted some information from the paper, because typing all this will require a lot of time, because a lot of notations, a lot of simples and a lot of equations are coming. So I simply this. So what is simple thing? So power law process is a very important model which are used for modeling repairable systems. Okay, repairable system means systems when you repair, when system goes off, you may repair, it start functioning again. That's how the repair, it differs from non-repair and a repairable system. So most of the system, fridge, freezer, TV, AC, computers, you look at the big end instruments, so they are all repairable systems. For any failure, you don't throw it immediately. You try to bring it into service by doing some maintenance or doing some kind of repair, some kind of overhauling, and etc. So that kind of systems are called a repairable system. So please understand. So most of this time, this exponential distribution, gamma, Weibull, and all, they are used for non-repairable, because items become IID. Whereas repairable system, the items do not become IID. Okay, so they may be independent, but may not be identically distributed at least. So there is a time dependence. So if the first failure will definitely have impact on the second failure, then third failure, etc. So it's actually a stochastic process. It's a Markov chain concept. Sometimes most of the time it can apply a Markov chain concept. So please understand that here is the failure, the items, the lifetimes depends on time. So that's why you have T1 less than T2 less than Tn as the first n occurrence times of random point process. So it's a point process model. Okay, with starting with T0 equal to 0. And you have a counting process. You will come to know how many failures are taking place between 0 to T1, 0 to T2, 0 to Tn, etc., etc. That's how it goes on. Okay, so you have a counting process, and that counting process is actually a stochastic process. Okay, so that counting process can be defined this way. Okay, you have n0 as 0, and ntt greater than 0 has independent increments, and probability that there will be a one increment, one occurrence is going to be sometimes lambda times t into delta plus order of delta. This is how we define the stochastic process. In the first class, if you have attended the stochastic process class, you might have been exposed to this kind of notations. And for two or more of occurrences, it is order of delta. So, but interestingly, if lambda of t is constant, that becomes homogeneous Poisson process. So here lambda t is important. So t, it depends on the time. And that's how, if that depends on this probability of stock in t to t delta t divided by delta t, and if you take the limit delta t tends to 0 in a short interval, what is that? So that becomes beta by theta t by theta raised to beta minus 1. It becomes the intensity function of the process. Okay, so it is what is called intensity function. This is just like a hazard rate when you talk about IID setup, but here it is not IID setup. Here is a dependency. So that's why it is called intensity function. Otherwise, they are same. But you have to to keep a very important distinction between this. Okay, here it is not IIDs. Okay, so that's how the whole process. So we have this interesting relationship. If you take the derivative of this, if you take the m of t as the expected value of the number of counts, that becomes theta raised to beta, and that theta that becomes the component of intensity function. And if you take the derivative of mt, that becomes the expected rate of occurrence. There are many interesting results. Let us look at some more interesting result. So as I already mentioned, lambda t becomes lambda is constant, that becomes the homogeneous Poisson process. And since it looks like a Weibull hazard function, so it is also called Weibull intensity. Okay, so but most of the time the scientists and statisticians use the term power law intensity. And this is how you can write down the likelihood function. That's what I want. If I get the likelihood function, I can do all the inferences. Okay, so you have, as usual, T1 less than T2, etc., Tn as the first Tn realizations. And likelihood can be written as simply product of lambda of Ti e power minus integral 0 to s lambda of T dt. Simply plug in lambda T as 1. So if you change the lambda t, you will get according to a different process. So here it is viable process or viable or power law process, viable intensity process. And you see that if beta equal to 1, the process reduces to a homogeneous Poisson process. So I'm getting a special case of homogeneous Poisson process, and I am getting two other cases also. If beta greater than 1, we say model is deteriorating. Means after a certain stage, the entire system will fail. Similarly, if beta is less than 1, it becomes, it actually models reliability growth. Means reliability will increase. Okay, this is how we interpret the value of beta. So there are three cases here. Beta equal to 1 is actually your exponential case. It becomes constant. Okay, so that becomes a homogeneous Poisson process. Now Poisson process. You just recall your stochastic process class in the first Poisson process when you learned. Okay, so the arrival times follows exponential distributions because it's homogeneous Poisson process. Because the time dependency goes off after a certain stage. So beta greater than 1, it's deteriorating. Beta less than 1, it is improving. Okay, these three cases are very, very important cases. And that's the reason why this kind of power law process is investigated for non-IID cases. So here are some interesting distributional results, which I am not discussing too much. You can also get into, but I will use the last relationship, that is f of t1, t2, etc., tn minus 1 given tn. I'm going to recall. Interestingly, you see that it is free from the parameter theta. So I have now two parameters, beta and theta. Beta is the parameter of interest. Theta is called, I will call for my research, I will call theta as the nuisance parameter. So I don't want the presence of theta. So how to get rid of that, I did a kind of conditional conditioning here with the last realization. Tn is the last realization. And under failure truncated data, you can easily get the maximal likelihood estimation. And please note, for viable distribution, you will never get a closed form expression for the estimates for theta and beta. You need a numerical solving of the two equations. Okay, that involves both the equations will involve theta and beta. And fortunately, for this distribution, this process, okay, this is not a distribution, I would say, this is a process, power law process. And for failure truncated data also you get, and time truncated data also you get the maximum likelihood estimation. So you may refer to the complete paper for more derivations and also yes. Look at the information function. Very interesting. Very. This needs a lot of derivations and all those things. All those derivations are shown in that article. Okay, please also note, you can see psi function existing. Psi function is that involves gamma, digamma, and all those things. Psi 1 is also there. So it involves a lot of gamma functions. And even we have inverted that matrix, that is also shown there. I inverse is also there. Even you can have estimate and the available information also. Okay, so what is important here? So you have already seen the model. So you have lambda t itself can be a constant, because if that is the case, that becomes the homogeneous Poisson process. Otherwise, it becomes a non-homogeneous or monotonic increasing or monotonic decreasing. So this is the first important aspects in this particular model. So here I will not show you why we need all this. I am not going to show it, but I will focus only on the score test on a later stage. Okay. So this is necessary. Trend testing is necessary because we have to see whether system is improving or not. Okay, it is showing any kind of stationarity or not. To see the successive intervals are independent or not. To check the time dependency of the interval, the intensity function, whether it is linear, exponential, logarithmic, or this. A lot of issues are there. So this kind of trend testing is important. So we have referred to many books in the literature and research papers. We have found some existing tests. Here is one test, very important test. That is what is called a Kramer-von Mises test, which is generally used as a goodness of fit test. In this case, again, we have a Kramer-von-Mises test. Military handbook test is another important and powerful test. M, that is equal to you can see that it's all involving TIs. TIs are the realizations. In most of the cases, both these cases, you can see nth realization is also coming out to be. How to do, how to reject, how to take the decision, etc. is all mentioned, and in which particular situation, which type of intensity function works well, that is also shown here. What will happen to the whole test statistics if t tends to infinity, that is also shown there. So please refer to the article. Okay, here is another test, Laplace test and a modified Laplace test. And here is another test which we have proposed. When I was doing my research, we have done with, I did my research with Jani sir and Shanbag sir jointly. They have guided me, and it was proposed in the year 1997. This is again a very important and a competing test. We have compared with all other existing tests, and we have found that this is the best performing test. Under H0, fortunately, we could find the mean and variance also in the closed form expression form. Okay, you can see what a beautiful form it is. Okay, so again, the test where power computation and all other comparisons, we have done it. You can refer to my text thesis also. You can also refer to many other papers also. We have already published a paper based on this also in communication statistics. Okay, so now I want to test for specific parameters. So in the earlier tests were only together for the intensity function testing, whether it is trend exists or not. Now I am going to be very specific whether the presence of beta in the presence of theta makes influence or not. So that is where I'm coming up with the test for parameters only. Okay, so likelihood as usual, I have shown already. Here is again 2.1. And interestingly, you can see that Tn and summation I is equal to 1 to n minus 1 log Ti become jointly sufficient for theta and beta. So this involves a lot of interesting estimation as well as testing aspects. So this is a very important conclusion from here. So I got the sufficient statistics for theta and beta. If I keep theta as known, so I get summation log Ti as my sufficient statistics for beta. And with that, I can play with some other inference that includes even testing also. Okay, so that's how it is going to be. And 2.2 also I have derived. I have already shown you there in the given Tn how it is going to be the likelihood. You can see that it is free from parameter theta. So with this, using this, I have exploited that for testing H0 beta equal to beta naught versus H1 beta greater than beta naught. Okay, and here is the test statistics which reject H0 if minus 2 times summation log ui less than or is equal to C alpha, where C alpha is such that probability that under, because you always to see that the probability under H0 that becomes alpha, okay, or size condition should be satisfied. This is how you verbally say, okay, the test statistics should satisfy the size condition. Okay. Now, if again I make a transformation ui is equal to Ti by Tn whole raised to beta, that become what is the pivotal quantity for beta. Okay, I is equal to 1 to n minus 1. Also, C alpha is alpha percentage where you can compare with the chi-square value for 2n minus 1 degree of freedom. All distributional results are also shown with proof also. So please refer to the book. One of the earlier paper, we have shown the complete derivation of the other property. It's a 1999 paper, slightly an old one. Okay, so again, that was a kind of uniformly, that's a powerful test. But here I am suggesting beta not equal to beta naught under H1. So we will definitely get a uniformly most powerful test. And we call it sun bias test. So we reject H0 for Vx, which is not in this particular interval. That is C1 to C2, where C1 is also calculated, C2 is also calculated. If it goes outside that where Vx is computed as summation I is equal to 1 to n minus 1 log Ti by Tn. So if Vx lies outside this C1 and C2, you reject H0. And both these conditional tests are similar to that of Bain. And we have compared this with the Bain and Engelhardt 1980 test, which is again a book, which a very important book in reliability studies. Okay, so please refer to that book. That book is also available in SP University library. And most of the libraries, they have, Bain and Engelhardt book is also available. The best book for repairable system studies. And we have compared that with their test also, and we found it is almost similar. So we don't need further investigation. Then from there, we have computed a large sample test based on substituting the MLE of theta, beta. Now, theta is now gone because we have conditionally, we have proved that it is free from parameter theta. So this test 2.5 becomes root n minus 1 beta cap C minus beta divided by square root of B. So beta cap C, that C stands for the conditional. Please note. This is a conditional test. The conditional based on that, you compute the maximum likelihood estimate. That estimate is substituted here. That is beta cap C. So that follows asymptotically normal with 0 and 1. And the beta cap estimate is also shown here. Okay, so now, I will show you the test based on likelihood function. So please note that I have given the A. Please note this A. In the table, I will show only A, B, C, D like that. I'm going to compare 5 different tests. This is one test which I'm going to cover. And 2.4, 2.5, I have not compared because already they're almost same. Like, so I don't need a comparison. Now, there are many other tests which I'm going to compare. Okay, so here, okay, so here again, I did a lot of manipulation and a lot of interesting theories into the test construction here. So here I prepared a fully a likelihood ratio function test kind of thing. So that finally going to be 3.1 n times I beta naught. I beta naught is the Fisher information. Beta naught minus beta cap follows chi square 1 minus alpha. Okay, now all distribution theory need to be proved here. So that's why I want you to see the research paper. You can get a complete derivation of all this. How under H naught that going to be chi square 1 minus alpha. Okay, so here now again I define mu t log mu t as log of the likelihood computed under beta and another under H naught, because likelihood ratio test needs a computation of likelihood under H naught as well as under H1. Okay, so the difference is what is called mu t, and the likelihood ratio test is computed. That is coming out to be 2 times log mu t greater than chi square 1 minus alpha. And again we have found some other interesting. I mean we have tried to see that log mu t has been expressed in terms of 2 components, u times v plus epsilon, and u and v are also shown here, with that both u and v contains information function as well as some kind of score function here. And n tends to infinity, u is finally going to be chi square 1, v going to 1, and epsilon going to 0. So you have finally a perfect test statistics expressed in the closed form expression, and that is coming out to be finally 3.2 something. Okay, so with some manipulation, simplification, etc., you finally going to be 3.2. Okay, you can see that all will involve some at least beta information functions. Now I'm going to define the score test now. Okay, again, further, I did a lot of other interesting manipulations with some substitution I see. So conditionally, I solved the information function for beta. That is coming out to be IC beta as n minus 1 by beta square. That is finally substituted in the likelihood ratio test. So which finally giving me 3.3, and some under H naught. Again, we did the estimate of that. That is beta is equal to beta cap C. We got finally a result 3.4. So this beta B, that I giving the notation here, I mean the equation number B, because I'm going to compute this also for comparison. Okay, so finally this 3.4 is also equation 3.5 is very, very important, and very important in the sense that you have a closed form expression. And this paper is very widely cited because we have provided almost all types of tests, and interestingly all tests have a closed form expression and with a distribution under H naught derived. Okay, so here is the test based on the score function. So this is the same score function which we have discussed so far. Okay, so the score function here, the H naught beta equal to beta naught against H1 beta naught equal to beta naught will reject H naught if 1 by n summation, that is d log L by d beta, that becomes score. So for single parameter it becomes square. So divided by I beta or I inverse beta naught, because it is can be easily computed because with one parameter, so I inverse beta 1. That follows chi square 1 minus alpha. And there again, we did not stop there. We have used many manipulations here. Unconditional score test is also computed based on the previous results. So you can see that involves that also involves psi function. So psi 1 also psi 1, that becomes the derivative of that. Psi becomes the digamma function. Okay, now 3.6 also depends on theta. Yes, to get rid of theta impact, we have used the conditional distribution 2.2. I have already shown you. And with that, you can see the result 3.7. Now look at the 3.7. That is now free from parameter theta. So theta, I want. So if the presence of theta always influence the test value and test power. So that is why I wanted to make it away. That's the reason why I have used the conditional distribution. So I have used explore that also, and I got equation 3.7. And that also, you can see the beautiful form. Okay, so if you look at, if you remove all those things, you can see summation log Tn by T1 coming in everywhere. So even in the previous cases also that is, but with some additional parameters. And these additional parameters, n, beta, naught, all will influence the power of the test. Okay, so C is also going to be computed, and you can see that the value of power is going to be extremely high for this particular equation 3.7. So C is going to be the one of the best performing tests. Okay, so I will show you the table also. Further, I have also used another theory which I have brought it from a research from a matrix algebra, that is Liang 1983. Suppose your information matrix is I theta beta, that is I theta theta and I beta beta in the diagonal, and I theta beta and beta theta on the off diagonal. They will be same, no doubt. Okay, so but when you have to write in this format. Okay, so here what I did was, I want the information about beta, keeping theta as a nuisance parameter. So I define I theta beta as I beta beta minus I beta theta, I theta theta inverse I theta beta. So this is to be computed, and this needs some detailed mathematical derivation. And you can see I theta beta I had already shown. This is the same thing which I had shown previously. Okay, so here again I want it, because this is simply copied and pasted here. Okay, so here is the 3.9 is the information about theta, ignoring the effect of beta, or leaving the information before. So that way also you can interpret information about beta, ignoring the value of theta. So you can see that expression n by beta square times 1 plus I1 n plus 1, that do not involve theta now, because that impact is gone. So this will definitely give me a new test which will again have a good power. So 3.10 is derived from this one. So D is also going to be compared now. So I'm going to calculate the power corresponding to D. So I have now 4 important tests, which is again all proposed by us. Okay, with some manipulations and important theory from conditional distributions, etc., etc. Even 3.10 is not stopping here. So I have used some, yes, all this gamma, digamma function can be approximated to first 1 term, 2 term, 3 terms, etc. And we have done some interesting mathematical manipulation here. So considering 1, 2, 3 approximations, so first term, second term, third term expressions, and you can see how it has simplified. And all these well-known results are well-known. And for using that also, we got a statistics 3.11. Because it is approximated, because we have not considered the complete term, so the power of this test is not going to be good. That's why we have not brought this into the table now. So look at the table now. Okay, here is the complete statistics, the power computation. Okay, so we have used simulation size 5,000. We started with 1,000, 2,000, 5,000, etc., and even more than also we have. But after that 5,000, we didn't find any difference, actually marginal difference. So we stopped, because stopping at a lower level, it become, you get the results fast. So we have stopped somewhere using 5,000 as simulation size. And theta we have assumed 10, alpha as usual 5%. So what you can see is all 5% level of significance, the power is computed here. So beta, as you can see, when it goes away from 0.4, or maybe from 0 or 1. So look at the first one. You look at this particular column, that is the beta equal to 1.0. So that is what is tested. Okay, so under H0, you are testing beta equal to 1. That means it becomes exponential distribution, or it becomes homogeneous Poisson process. So under H0, if you compute power, that becomes alpha itself. That is why you can see the whole column, you can see it is going to be close to 0.05. So you can see 0.045, 0.046, 0.51, etc. So please look at that column first. Okay, so the fourth column rather. Sorry, the fifth column, beta equal to 1. You can see, because under H0, if you compute power, it is going to return as the significance level only. So we have kept a significance level alpha equal to 0.05. So you have beta as 0.0505, almost. As the sample size increases, and at 10, 20, 30, you can see it is going to be perfectly 0.05. So that means the test is unbiased, and performs consistently well. Now look at beta less than 1. So all those values, beta equal to 0.4 and 0.8. You can see how the power varies and power increases. And similarly, beta equal to greater than 1, that is 1.5, 2, and 3. But you can see how it varies. Naturally, because you are leaving away from the H0. Okay, H0 is beta equal to 1. And you are leaving away from either side. Less than also, greater than 0, definitely power will increase. Now look at the equation C of all the rows. Okay, in all the rows, you can see that is the score test. The power corresponds to the score test. I can see the equation C in for n equal to 10 also, 20 also, 30. You can see the maximum power when you compare with all other A, B, C. There's another existing test. We have done the study after 2000, somewhere around 96 or 97 or something after that. There was an important test, as I told you, BE. BE stands for Bain and Angel Hut. Bain and Angel Hut. That's the test which was there in the literature that was used by till a period. So we computed that also power for that also. It's not bad. It is also good. But still, if you see equation C, the power corresponding to equation C, that is much better. And even equation D is also somewhat better. I mean close or at least at par with the BE test. But equation C is extremely performing well in all the cases, sample sizes. If you increase the sample sizes, probably you may get the best power. And if you see beta, the more you go away from 1, the power become more and more. It will touch 1. You can see beta equal to 3. You can see it is very far off from 1. So the beta is now becoming almost 1, 0.94, 0.92, something like that. Okay, so this is the power computation. So it really makes sense to believe that the Rao score test is the best. Okay, let me show you very quickly in another 5 minutes. I will stop, don't worry. 2 numerical examples we have presented here. In the same paper, you can see complete details. Okay, so we have taken one example from literature, that is by Kumar and Klafjo. They have compared many machines. LHD1, LHD. These are all very big machines used for, these machines, what you say, this used for road roller and all those things, that kind of big machines. They compared whether the failure pattern follows a particular distribution. They found they have considered 7-8 machines, I think. Okay, the number LHD1, 3, 9, 11, etc. So some 19 machines and 9 machines we have compared, and we found that in 3 cases it follows power law process, and some cases they do not follow power law process, and therefore we have computed the power also, and you can see the estimates also. The last line, not the last line. Yes, last line you can see the p-value correspond to the test. So they are following the power law distribution. So the machines 1, 9, and 17. So that's why that kind of things we have done it. So please refer to this detailed discussion we can have. Another example is from a real life example which I myself have collected when I visited the Visakhapatnam steel plant, where they use big dragon machines for transferring big items and machines to some other places. So they have a very important this thing. So a good friend of mine working as a material and manager there, so he invited me there, and I myself presented there. I stayed for 2-3 days to collect the data. And we found he was also working on this kind of power law process models. So this is something which I myself experienced to the data collection, and it was really interesting thing. So we found the PLP was very suitable with the theta estimate as 4.804 and 1. We did collect the observation for 2 continuous days, and we got around 1,700 something observations. So that all data we have. We have written here also that it's also available with the others. So you can, if you are interested, I can show you the data. So the computer power is also there. So we have got the power as 0.876 for the same score test, and is coming, p value is also coming out to be 0.06. So it's a perfect setting for low 0.87. So there is no doubt about the importance of saying that a score test is Rao score test is the best. So if you wanted to compile all in one, so the contributions can be unified as in say his information theory, geometry, estimation, and asymptotic inference. So he has contributed in all. So today the Rao score test become an indispensable tool in many scientific disciplines. It's also widely applied in generalized linear models, logistic regression, survival analysis, genetic association studies. So that's why I brought that kind of logistic regression based example. econometrics, reliability engineering, and the detection of weak signals in particular physics and astrophysics. So I have shown an example based on physical experiments. So its computer efficiency and strong theoretical foundation make it one of the most powerful methods in modern statistical inference. Thank you very much. So here is my books. If you are interested, please refer to these 3 important Springer published books. Okay, so you can see, you can purchase, you can at least get the book, at least 1 copy at your library if you can possible. I request our head of the department, Dharmesh Kondale, to have 1 book, at least a copy of it. These are the 3 Springer books. And this book I had already shown you, Parametric Inference. The international version is also available. And my first book, Statistical Methods for Quality, Reliability, and Maintainability. This was meant for, is still meant for Six Sigma professionals, engineers, especially mechanical engineers people. And statistics students can also use this book. And this is very cheap. You can get it for 340, 330 rupees or something like that. So please get it. Thank you very much. There are some of the references used in the research paper. And I also request you to have a watch on my video. It is titled as Elucidation and Interpretation. Thank you. Any questions?
Yeah. Thank you very much, sir, for your insightful and inspiring lecture. We would like to open the floor for the few questions. If anyone has any question, please feel free to ask now. Kindly raise your hand virtually or type your question in the chat box.
Right. Please, I am waiting for some questions. I really want some questions from your side. Students especially.
Yeah, anyone from audience? Students? Yes.
Yes, students. Anyone, please.
Yes, students. Anyone?
Thank you, madam. Nice to see you.
Yeah. Reviving C.R. Rao very beautifully today.
Thank you so much.
I just want your comment on this.
Yeah.
That can we say that just like axiomatic definition of probability shared by Kolmogorov is a framework for developing any probability function, rather. So is it like this score test can also be seen as a framework to develop test for some
Madam, yeah, that is again the simplicity of the particular concept. So instead of framework, what it need is at least first and second order derivative should exist for the likelihood. That is most important.
Yes.
Because one comes for, one is required, the first derivative is required for score function and the other one required for that is the only regularity conditions required. When we talk about Kramer-Rao inequality, there, if you record, when we simplify, derive the whole thing in the class, we bring a lot of regularity conditions. If you see that, it doesn't work for densities which are open interval. So we need all, just like in a uniform distribution defined in 0, theta, that kind of conditions will not work. Probably here again, for that kind of distribution, that means we call it as Pitman's family kind of distributions. This will not work. That is, I think, that is the only. It's a very small point as such. Otherwise, all other family you talk about, you can construct a score test.
Okay. And here you mostly give examples where you have a simple distribution, but if it is like compound distribution, then also
it will work. I'm sure for compound distribution, mixture distribution also, and mixed in an appropriate proportion. I'm sure you can get. Even if it is not in closed form expression, you can calculate the first derivative numerically. And second derivative also numerically. So constructing a test strategies probably visibly may not be possible. You may need some numerical calculation. That's all. I'm sure it will work.
So thank you for the clarification.
Yeah. Here is another question which I received from Shay. What is your question? Repeat. Just
Sir, can we extend this Rao score test for any event related to spatio-temporal events by replacing theta with s is equal to space and t is equal to time?
yeah, stress strength reliability. If you that see, I think we should try, but that comes when you say probability range greater than y, that means stress exceeds strain or strain exceeds stress, whatever way you wanted to say, that is computing ultimately a probability, right? So when you write this as a model, it's actually coming out to be a number actually. Okay, so you are not getting a model as such. We need actually a model which we can be from there. You can go for first derivative, second derivative. So that is simply a number. Yes. Any other questions?
Any other questions from the audience virtually? Thank you so much, sir. Today's lecture provided us with a comprehensive understanding of Rao's score test, one of the landmark contribution of C.R. Rao to the field of statistical inference. So we learned the score test is a powerful method for testing of hypothesis by using slope or score of the likelihood function under the null hypothesis. So sir also explained the theoretical foundation of the score test, its relationship with the likelihood ratio test and wall test. So sir has discussed the power law of process, which is a statistical model used in reliability engineering to describe the occurrence of failure over a time when failure rate is changing. So it is one of the most widely used non-homogeneous Poisson process model. So thank you so much, sir, on behalf of Department of Statistics, Sardar Patel University. I express our sincere gratitude for your excellent presentation. Your explanation of the theoretical concept, practical application, and significance of Rao score test are greatly our understanding that the way you connected the contribution of C.R. Rao with modern statistical inference was truly inspiring. So your vast knowledge, rich experience, style of presentation have made today's session both informative and memorable. So I'm sure that all the faculty members, research scholar and students have gained valuable insight with benefit them in their academic and research journey. Once again, sir, thank you for sparing your valuable time, sharing your expertise with us. We look forward to many more opportunities to learn from your wisdom in the future. I would like also express my sincere thanks to our Honorable Vice Chancellor, sir, Professor Niranjan P. Patel, for his constant encouragement and support. My heartfelt thanks to also go to Dr. Dharmesh P. Raikondalia, Professor and Head Department of Statistics, for his guidance in organizing this lecture series. I am also very thankful to all the heads of the department from various University of State. I extend my gratitude to all faculty members, organizing committee members, research scholars, students, participants from various universities, which has made today's program great success. With this, we come to the end of today's session. Thank you everyone for your active participation. Wishing you all the wonderful day ahead. Before we conclude, I would like to make an important announcement. All the participants are requested to kindly fill out the feedback form after the session. Your valuable feedback will help us to improve the future programs. So participants who successfully submit the feedback will receive an e-certificate of participation. So once again, I sincerely thank you, our distinguished speaker, Professor K. Muralidharan, sir, for his excellent and inspiring lecture. Thank you so much, sir. We will share the feedback form link, please, all the participants. And we will show you the e-certificate also here. Just all of you fill the feedback form, you will get e-certificate immediately.
E-certificate immediately. Okay, madam. Can I leave or should I stay?
Sir, just wait for a few minutes, sir.
Okay.
Sir,
So thank you, Muralidharan sir. This
Thank
is
you very
a
much.
certificate of appreciation
Oh,
from
very good.
Department of Statistics, Sardar Patel University.
Thank you so much. Thank you so much. Oh, very nice.
Now I will also share to you, sir, and
Okay.
we will also share the QR code. So everyone, please scan it and fill the form so that we will share the e-certificate to you.
That's fantastic. Fantastic.
Thank you, everyone.
Thank you.
मुरलीधरन सर, आपको लीव करना है तो आप लीव कर सकते हैं.
Okay.
मैं बाकी
Thank you.
के फीडबैक करवा देता हूँ.
Thank you very much. Okay.
रिकॉर्डिंग स्टॉप कर दो. Stop recording and share.